I learned that it's not the prompt. Real GenAI requires real code. Let me prove it with an example from real world enterprise project. You are given a large enterprise database and you are asked to build a GenAI chatbot that can answer things like what were our sales in the last quarter, list products with declining year on year revenue, and show me monthly trends. So you do the usual, you build a RAG pipeline, you write beautiful RAG prompts, you feed your data frame to the LLM and expect the chatbot to behave. And then hallucination hits you in the face. Suddenly, the chatbot starts to invent numbers, make up trends, and confidently output wrong financial data. This is totally unacceptable for enterprise use. This is the number one pain point with LLMs today. They make things up even with good prompts. So, how do you fix it? You don't rely on one LLM agent doing everything. You split the process into two or more agents, each with a smaller, clearer job. Here, I'm using two agents. Agent 1 filters and extracts only the relevant data. Agent 2 aggregates, checks, and produces the final answer. This simple multi-agent workflow reduces hallucination, reduces context size, reduces token costs, and increases accuracy massively. One solution and four big wins. Now let me show you exactly how to implement this step by step with a sample code example using GPT 4.1. I will explain every line of code in this notebook, but first look at this sample question and the response. Here I am asking who lives in New York and what are their hobbies based on this data. So in the first step, the LLM agent 1 identifies what are the filters present in the question. It figures out that the filter is for the city column and the value is New York. Using this information, the data is filtered by a Python function. So instead of the original 4 rows, now I am using only 2 rows that are sent to the second agent. Now the second agent will just use the filtered data and generate the answer for the question that Alice and Charlie live in New York and Alice's hobby is reading while Charlie's hobby is sports. Now I have used a small data here intentionally to help you visualize the process. Of course, the LLM will not hallucinate on 4 rows of data, but when you have millions of rows and hundreds of columns in the enterprise datasets, then you will see the hallucinations a lot. Let's go through the whole code line by line and understand how exactly this result is produced. In this section, we are importing the necessary libraries. JSON will be used for formatting the outputs. We will use pandas for data frame creation and OpenAI for LLM calls. Please input your own API key here. You can get one easily by registering for a free account on openai.com. In this section, we are defining the tiny data frame with 4 rows using the pandas data frame function. We are passing the data in the form of a dictionary. Keys are the column names with corresponding values for that column. Please make sure the number of values in each column is the same. Otherwise, you will get a value error like this. Now in this section, we are defining the first agent. The role of this agent is to just extract the filter and entities from the question and nothing else. So we define our function agent1 extract entities and filter, which takes two arguments, the question asked by the user and the data frame columns, name, city, age, and hobby. Here we are defining the prompts for the agent 1. We use triple quotes for defining the prompts so that single and double quotes can be used inside it. The task assigned to agent 1 is to identify the relevant entities, their values, categories, attributes, etc. present in the question, and then decide how to filter the data frame using those entities, and return a Python dictionary with two keys. The first one is filters, a dictionary of column name versus the values, or the list of allowed values. The second one is reasoning, the explanation of how the LLM chose the filters. Then we provide an example of the output. This is also known as one-shot prompt because we are providing only one example. And this is sufficient in our case because our output format is fixed. If there were multiple different scenarios of the output, then we will have to provide multiple examples, and that is known as few shot prompts. We pass on the data frame columns in the prompt as well, which is coming as an input to the function. One important thing to note that passing just the column names instead of the whole data frame reduces the input token size by a significant amount. And this is going to play a massive role when you are dealing with datasets having millions of records. Here, we are using the LLM client object that we have defined above to make the API call for the GPT 4.1 model from OpenAI. The method used over here is the chat completions create method for the GPT 4.1. The model argument decides which LLM model to call, and the messages argument sends the prompts to the LLM. Like here, we are passing the instructions to the LLM using the system role and the user question using the user role. System role gets higher priority and it is reserved for specifying the rules and instructions to the LLM that it must follow. And the user role is reserved for passing the questions asked by the user. You can pass both of them together as well. However, it is not a good practice because we want to control how the LLM behaves. For example, if the user says delete all the rows from the data, then the LLM will look into the system prompt instructions to see if I'm allowed to do so or not. If the system prompt says that you cannot delete any data, then even if the user asks, the LLM will not delete the data. That is the reason both of these roles exist, and you must use them to define the correct LLM behavior. In the end, we are returning the LLM response, but before we return it, we need to convert it into a Python dictionary. Hence, we are using json.loads function. This is required because we are filtering certain parts of the response in the chatbot pipeline in the below code. In this section, we are defining two functions. First one is agent to answer that determines how the second agent will use the filter data frame and produce the final response. The second one is apply filters function that defines how to filter the original data frame based on the filter conditions found by the agent 1. Now look at the prompt instructions to the agent 2. We are saying you must use only the filtered data to answer the question and be concise and helpful in providing the explanation. Within the prompt, we are passing the filtered data frame as a string. This was one of the inputs to the function. Here also we are invoking LLM chat completions create method. The model we are using is GPT 4.1. Under the system prompt, we are sending the prompt instructions, and under the user prompt, we are sending the question. Based on these, the LLM will produce the response, which will be a string as seen here in the end. This is why there is no need for any type of conversion. Like in the first agent, the output was a JSON. Hence, we converted it into a Python dictionary using json.loads function. Now, the apply filters function is defined to filter the relevant data using the filter conditions identified by the first agent. So we are passing the full data frame and the filters as arguments. The first thing we are doing here is to create a copy of the data frame just to keep the original data frame safe. Now we will check the filters for every column using a for loop. If you look at the structure of filters returned by the first agent, it is a Python dictionary, and that contains the column name as keys and the allowed values in place of values. If there are more than one values to be filtered in a column, then it will come as a list. Otherwise, it will be a single value. Hence, we are checking if the filter values is a list or not. If yes, then we filter all the values using the isIn function, else just filter the single value. Once the data is filtered for all the columns using the for loop, Then we are returning the filtered data. This completes the logic to filter the data. Now in this section, we are defining the complete chatbot pipeline. We define the multi-agent chatbot function. It takes the user question and internally it will call agent 1, agent 2 and the data filter function that we have defined above. So first we call the agent 1 extract entities and filter function. It takes two arguments, the user question and the list of column names. The result from this function call is stored in the result agent 1 object and we extract the filters and reasoning from it in separate objects. In the next two lines, we are printing the filters and the reasoning for why these filters were selected. Next step is to filter the data frame based on the filters using the apply filters function. Now the last step is to pass the filtered data frame and the user question to the agent 2, which produces the final answer that is returned in the last line. Now, take a moment and pay attention to the fact that there is zero LLM token usage when you are filtering data in this second step. This is a very crucial step because if you blindly pass the whole data frame to the LLM and ask it to perform the data filtration, LLMs can do it for you, but at a high cost of tokens and very likely hallucinations in the final response. So we do this data filtration step using the Python code and not the LLM so that we can control what data gets selected. In this current design, we minimize the token usage because the first LLM call here only takes the question and the column names instead of the full data frame. And the second LLM call only takes the filtered data frame instead of the full data frame. And because we are passing the correctly filtered data frame to the second agent, we are eliminating the chances of hallucination. So here I am just printing the data frame for our reference. Let's run another question. Who is 25 years old and what cities they are located in? So agent 1 found that filter needed is age equals to 25 years. And it provides the correct reasoning behind this decision as well. Based on this filter, the original data frame is reduced to 2 rows and it is passed on to the agent 2. Agent 2 now provides a correct response regarding the locations of Alice and Sam. Now, you could have used multiple agents and still encountered hallucination if this data filter step was not used, which is a pure Python programming solution and it has nothing to do with the LLMs. So the important thing to remember is that just prompting the LLMs cannot solve all the problems. You need real Python coding skills to produce practical solutions. And I hope this chatbot multi-agent architecture is clear to you. Please try this out in your projects and let me know if it worked out for you in the comments of this video. I have given this notebook in the description of this video for you to download and play around. If you found this video helpful, then please share it with your friends and subscribe. This is Farooq Hashmi from thinkingneuron.com.